Okay, great. Yeah, so we're very happy to have Catherine Ray in the Topology and Geometry seminar, who will be talking about inverse Galois theory as Thor's hammer.
Yes. Hi, everyone. So I'm not exactly sure what the background of everyone is. So what I understand, this is like a general topology seminar. So I thought I would kind of, yes, okay. So inverse Galois theory as Thor's hammer. And what I mean by that is that we're going to use, so what is inverse Galois theory? Well, it answers the following question. If you have, given a group G, is there, well, I mean, it depends on what generality you want to ask it in, but let's just say this. Is there a field extension L over K such that the Galois group of L over K is G? Okay, and this is going to kind of come back later. But I just wanted to give that little brief overview of what inverse Galois theory is. And in particular, the story that I'm about to set up has the following motif. So the motif is a classic one that we encounter a lot in algebraic topology. And the motif is that there's a space X and a group G that acts on X. Oh. So then we can ask, what is the cohomology of G acting on X? Oh, something happened. Can you still see my screen? Okay, sorry. There appears to have been some error that occurred. Oh, the tablet got disconnected. Well, that's unfortunate. But let's see. Okay. Let me try to join one more time with the tablet, and if not, I have kind of slides that we can default to. Sorry for the technical issues here. Okay. I'm not really sure what's going on with that. Let's see. All right, I'm going to use these older slides because that's not working out. And hopefully that will not cause an issue. All right. Can everyone see this? All right. So here are some old slides. They have things written on top of them. I apologize for that. All right. So motivating vibes. As I said, there's this motif of we have a group acting on a space, and we want to understand the cohomology of that group acting on that space. And now I want to give you a bit of context for why we would care about the particular group and space that I'm going to talk about. Now, for those who happen to know this group and space, what will we be will be talking about is the Lubin-Tate action. And the Lubin-Tate action is an action of what in topology we would call the Morava stabilizer group on the Lubin-Tate space. But let me set up like why you might care about this group action and why we might try to calculate the group cohomology of this group action. Now, if you have kind of a more arithmetic background, it happens to be the case that this group and this space come up in trying to understand isogenies between abelian varieties. So for example, if you have an abelian scheme and you want to look at all other isogenies to another abelian scheme, you can look at like pairs of abelian schemes that are isogenious. You can have two maps down, which is projection on to like the first abelian scheme and the second abelian scheme. And then if you start with one abelian scheme, you can ask, what are all of the other, I should also mention that an isogeny is a map between abelian schemes which has a finite kernel. So you can ask, given a group G, what are all of the other things that are isogenious to, given a group G and an abelian scheme, what are all of the other things that are isogenious to that abelian scheme with isogeny, with kernel that isogeny group? And this will allow you to start with one kind of abelian scheme, look at all other abelian schemes that are isogenious to it, and project down to that group. And this kind of means that you can start with one cockroach that's like living on the moduli stack of all abelian schemes and spread it out to all of the other ones that can possibly be isogenious. Anyway, that's just the vibe of what a Hecke orbit is. The Hecke action is the action of starting with the Hecke action comes from just trying to understand how abelian schemes associate with each other up to isogeny, but I'm going into way too much detail for a motivating vibe, especially in a homotopy talk, so let me move on. The one that is perhaps more familiar to you all, or at least perhaps closer to you, is what shows up when we're trying to calculate the homotopy groups of spheres. So this group and the space show up as the E2 page of a spectral sequence that converges to this thing that is called the like localized homotopy groups of spheres. And the idea of this localization is the following. If you try to calculate all of the homotopy groups of spheres, it ends up looking like an absolute chaotic jumbled mess. I mean, this is just like, there's no pattern that you can really see. I mean, it's just like, it's completely unperiodic in every way. It's just like the digits of pi. However, we discovered that if you can kind of apply these bandpass filters to like limit what you can see, like instead of a radio signal playing all of the channels at the same time, you can listen to the individual voices. And this is kind of what we call the local homotopy groups of spheres, and the localization is at what the analog of what a prime should be for a space. So the E2 page of this is the group, and this is the group cohomology of the group in the space that I'll be talking about today. And this group action is super mysterious. We've been using the same limited info about this group action for the past 20 years. And now we have more information. Yay! So I'm going to talk more about that. Okay, so here's the idea of what I will be talking about. And then afterward, I will define everything. All right, so let's say we have a homotopy. Let's say we have a formal group of height h over a characteristic field P, and this is just some object. This is some group scheme. This is some space, if you want to think about it that way. Now we can consider the automorphism groups of that object, and we can look at subgroups of that automorphism group. So now we can ask the question, if we have a moduli stack which satisfies some properties, then we can actually kind of really pin down this group action that we're trying to understand. So in other words, we have a group that's acting on a space. I have not defined for you the group or the space. Now, the group that I will kind of get to the full definition of is the automorphism group of this thing called a formal group, which I will tell you more about. And what we want to understand is the action of this on the kind of deformations of this object H. And the idea is, well, if we try to just understand this action as it's stated, it's way too floppy. Like we can't really work with it. And so what I did is I showed, well, we can actually craft this really floppy situation into a very geometric one, which we can try to understand. And then when we pin down the action geometrically, just the natural projection down is the correct group action. So great. Now, I will define some stuff. Okay, so if you checked out because I was rambling a bunch, please check back in because now I will actually define everything I'm talking about instead of just waving my hands. So let's define some stuff. Okay, so what is Lubin-Tate space? So Lubin-Tate space is this space that comes from understanding the notion of a formal group law. So a formal group law is essentially the analog of a Lie group, but in characteristic P. So Lie groups over RRC in characteristic P become kind of smooth algebraic groups. And just understanding the tangent space of the Lie group, which allows us to kind of reconstruct and work with it, in other words, the Lie algebra, becomes understanding kind of the full Taylor series. So like the jet bundle at the identity of the smooth algebraic group. So it's the completion of the identity section of the smooth algebraic group that is equivalent to, instead of just looking at, as I say here, the first infinitesimal information, just looking at the tangent space of the kind of Taylor series expansion, you take the entire formal group, the entire formal power series, the entire Taylor series expansion. One way you can think about that is if you're trying to understand anything which has, x to the p in it, in characteristic P, when you take the first derivative, it becomes P times x and it becomes 0. So if you want to understand P powers and characteristic P, you have to look at further derivations. Okay, so what is a formal group law? A formal group law is a power series which has some group properties. What I mean by that is, I don't know if you can see my cursor. Let's see, maybe I can, you can see my cursor? Okay, great. All right. Oh, and it appears I can also annotate. Great. So let's define what a formal group law is now that we have this kind of vibe that it's supposed to be the analog of a Lie group in characteristic P. What does that actually mean in a way that we can work with? So what that means is that if we have a power series in, two variables, which I'm going to write this way, we can ask for that power series to have like groupy properties. So we can ask for it to satisfy, for example, the distributive law. That is, if you first look at the power series in two variables and then look at that as the first variable of the power series with another variable, then this is the same as doing it alternatively. And we can also ask that, for example, putting 0 here will return for us just x. So it has an identity property. So a formal group law is a power series which is behaving as a group operation. It has the distributive property and it has the identity property. And the ones that we will be working with are also commutative. So it means that if you start with x and y here, like so that x plus y, with plus being this addition being this whole power series, is the same thing but with y and x switched. Okay. Great. So does anybody have any questions before I kind of scroll on? I'm now gonna kind of sorry?
I have a question.
Yeah, go ahead.
If I took an algebraic group and then I looked at the like the functions on the formal neighborhood at the identity, and then I looked at the multiplication, like what the multiplication induced on that.
Yeah.
Is that what the formal group law is?
Yes. Mm-hmm.
And the reason that people consider this is because Lie's theorem fails or something for algebraic groups. Is that?
So what is Lee's theorem?
Oh, like the correspondence between Lie algebras and Lie group that you can always.
Yes, exactly.
Okay, thanks.
You're welcome. Sorry, I interrupted you before you finished it. You can always kind of recover the Lie group from the Lie algebra is what Lee's theorem is, right? Yes.
Yeah, or that there is a group.
Yes. Yes. So it fails in characteristic P, and so we have this other circumstance which I guess gives us Lee's theorem in characteristic P. Sorry for interrupting you. Okay, great. All right. Oh, and I can't scroll now. Well, that's bad. Truly, today has been a technological. Okay, great. So as I said, these are old notes, so they have old annotations on them. All right. So now moving on from the notion of formal group, which I could give more examples of, but I think I will instead try to soldier onward, given that we're 20 minutes in. This is a 50-minute talk, is that correct? Okay, great. Okay, so I do actually have at the top here some examples, so let's just look at those. As whoever just asked that question stated, these formal groups can come from kind of completing an abelian group scheme at the identity. And sorry, I'm trying to draw here. So an example of if we take the additive group scheme and we complete at the identity, we get x plus y, which is, great. And if we take the multiplicative group scheme and we complete at the identity, we take this shift. So essentially we're taking x. You could ask, okay, why isn't the additive group scheme's formal group law just x times y? And the answer to that is if we added 0, we would get 0. So that is like x plus y in the additive group scheme. If that was x, would be x times y, which would be 0. And so it wouldn't have the property that x plus 0 is x. And so this is this kind of shift there and shift back is allowing us to have an identity. Okay, great. So those are two examples.
Sorry, Catherine. There's a question in the chat. If you look at the
sorry.
Properties of a formal group law, it looks like the equations of a monoid.
I'm sorry, I can't. What was
right?
The
so if you
question?
look at the definition of formal group law, it's reminiscent of just the equations for a commutative monoid. And do we get negatives for free in that context?
So, negatives. Oh,
Yeah.
like, are you asking if it's if there's like an invertible power series situation there?
Yeah, is there a minus x sub f, right? A formal negative.
A formal negative. There should be a formal negative, I think. So I guess the reason I'm thinking this might be the case is that, so for example, you can always construct a formal group law. So if you take it in an invertible power series, you can always consider a formal group law in the following way. You can think about it as you have an invertible power series that's in one variable, and you take that invertible power series, let's call it f, or I guess f is the name. Let's try that again. Maybe call it h. And then we can take h of x plus, and this is the actual plus, h of y, and then take the compositional inverse of that, h inverse of that whole thing. This will be a formal group law that satisfies the constraints that I said above. Sorry, it's not allowing me to scroll again. Oh, there we go. And so in that context, wait, that still doesn't give you if you have a minus x. I do think you should be able to have one, but I don't immediately see why. But maybe I can think about it and send an email to whoever asked it. Okay.
Thank you.
But I do think it's true. I don't immediately see why it should be true. All right. Okay, so now. All right. So we have this notion of formal group law, which is our analog of Lie algebra and characteristic P. And if we consider, Artinian complete local K algebras, in other words, we want to consider kind of local K algebras that aren't too terrible. So for example, if you're not super familiar with like local K algebras or whatever, if we take FP and you want to consider what is like a local FP algebra, an example of this is ZP, so like the p-adics. So whenever you see R, like an R here that's coming from an Artinian local K algebra, you can just think about this as being the p-adics and the K here as being FP. This is like not going to really remove too much of the point. All right, so if we have a formal group law over a characteristic P field of height H, then we can consider the deformations of such a thing. And these are...
Sorry, Catherine, do we insist on it being Artinian though? So do you want to remember really all the truncations of ZP? Like a formal inverse system? Of ZP modulo P to some power? Or... So I'm worried about the Artinian conditions.
Yeah, I think what you're maybe... Oh, you're saying ZP isn't necessarily Artinian.
Where I'm worried about that part, yeah. But I guess if we remember all the high enough or arbitrarily high truncations that should be the same information.
Yeah, I think we can, instead of taking Artinian algebras, like into Artinian local K algebras, we can just take complete local K algebras, and that this is fine. Later we're gonna have a situation where we want to look at if like a functor is representable, and in order to talk about it being representable, we'll have to move to the pro category of Artinian local K algebras anyway.
I see.
I think this will get rid of your question.
Yeah, so it should be fine. Yeah, thanks.
Yeah. So I guess the answer is, well, ZP isn't actually an Artinian K algebra, but what we're really considering is pro Art K. Just to reiterate my answer to Martin's question. Okay, great. So now if we want to look at deformations of, we have a formal group, let's deform it. Okay, so what are deformations? Deformations of a local group, of a formal group that's living over a characteristic P field are a formal group that's living over a, let's just say, complete local K algebra. So for example, ZP, as well as a way of reducing the larger complete local K algebra to just K. So we have to also remember that information. Okay. And so we have now this functor, which is deformations of R. And we have an action on this functor by the automorphisms of the original formal group, which we deform. And this action acts by precomposition here. Hopefully you can still see my cursor on iota. So we go from having this isomorphism of H with kind of this reduction of the formal group from this, ZP to FP. And now we can change this isomorphism by precomposing with an automorphism of H. Okay, so this is the action of the automorphisms of H on the deformations of H. And now we come to the answer that I just, the kind of correction that I just gave Martin, which makes this, the statement can be said much more simply than I've stated here, which is that this functor, which is a functor from complete local K algebras to groupoids, although if you're not comfortable with those, you can just think of it as sets, but it is a groupoid valued functor, that this functor is representable. And what that means is that if we want to look at deformations of a formal group over a local ring, we can just look at homomorphisms from some other ring to that local ring. And that local ring is is the vit vectors adjoined a bunch of power series variables. If you've never seen the vit vectors before, I will again have you ask of them. So if you take K being FP, you take the vit vectors of K, this is ZP. So if you've never seen the vit vectors before, you can just substitute thinking of them as ZP. And I'll just briefly say that the vit vectors are kind of a nice way to give ring structure to things. And that's kind of the purpose that they serve. But here again, just substitute W of K to be, ZP associated to FP. Okay, so
How does LT depend on H?
Sorry, say that one more time.
How does LT?
How does LT okay, so the dependence on H is hidden in the big H. So big H is a formal group of height H. I have not told you what height is. But so H is a formal group, and it has so formal groups over characteristic P fields are all isomorphic up to 2 invariants. So if you have a formal group over a characteristic P field, all of them are isomorphic if they have the same height. So height is a complete isomorphism invariant. I have not defined for you what height is, but H here is the height of the formal group H. I realize that calling them both H is a bit confusing, perhaps. All right. So Lubin-Tate space is something that depends on the choice of the formal group. And it doesn't depend on the choice of formal group. I mean, it depends, as I said, formal groups are isomorphic up to height and prime. And so given the characteristic of the field, the space of Lubin-Tate space is dependent on both this prime and the height of the formal group over this. The height is any natural number. And I can say kind of a bit about what height is. So I really wish my iPad was working for this, but I will see if verbally doing it will suffice. So height can be defined in 2 ways that are equivalent. I think the easiest way to define height, given that I've been talking about formal groups in this power series format, is the following way. If you take the P series of a formal group, so for example, so the P series of a formal group is taking, X and adding X to itself P times. So taking, P times X, or like N times X if X is some natural number, for example. And so if you do this for the additive group, it's just X plus X plus X, X plus X, and this is, P times X. If we do this for the multiplicative group, it's X minus 1 to the P plus 1. And if you're over F of P, this is just X to the P minus 1. And the height is the first non-zero coefficient of the P series. So if you take the P series, it's going to be, just adding X to itself P times. And the first non-zero coefficient will be, the P series will always be a power series in one variable with non-zero coefficients only in front of X to the P to the I. So we have these AIs over X to the P to the I, and the first non-zero such I is the height. So in the additive group case, since we're looking at P times X over a characteristic P field, the height is infinite because there is no non-zero coefficient. And for the multiplicative group case, the first non-zero coefficient in front of a power of X is the first power of X because it's X to the P. Another way of thinking about this is if you take, which I think is a little more intuitive, is if you take an abelian group scheme and you look at the multiplication by P map on the abelian group scheme, and you look at the kernel of this map, you ask for the rank of the kernel at the identity. It's going to be a power of P, and you ask what power of P that is, and that's the height. The reason that I gave the P-series explanation is that you can do without thinking about it as coming from an abelian group scheme, but all of the formal groups that we're going to be working with, we're thinking of as coming from abelian group schemes anyway. Okay, great. So,
GM and GA are different in characteristic P, which I guess is not, I mean, locally, like in characteristic 0, they would be the same.
So GA and GM are isomorphic in characteristic 0 by the logarithm map. In characteristic P, the logarithm, I mean, you have to divide, like the power series for the logarithm map requires you to divide by P. So it is no longer an isomorphism in characteristic P.
Okay.
Yeah. I agree in characteristic 0. In characteristic 0, they're all isomorphic. They're all isomorphic, but not in characteristic P. Okay, so
Sorry to, can I just ask one more question?
yeah, you can ask as many questions as you'd like, being who yeah.
The classification in terms of the prime and the height, that's because we're assuming commutative, right?
Yes, although commutative is actually enforced by identity and distributivity if your group scheme that you're working over, if your like coefficient ring is non-nilpotent. I mean, so we are assuming commutative, but I'm just saying that commutative is actually enforced by the associativity and identity conditions if you're working over a non-nilpotent ring. This is non-trivial, I'm just mentioning it.
But then the dimension is one, like the dimension is 1 as well.
Sorry. So these are I'm talking here about one-dimensional formal groups. So yes, the dimension is 1. I mean here that I'm not asking for tuples of x and y. I'm saying just x and y as variables. So they are one-dimensional. And so GA here I'm thinking of as, the underlying group scheme is A1. Similarly, GM is A1. Okay. Okay, so Lubin-Tate space. I mentioned at the beginning that there's this motif. The motif being there is, this motif, a tale as old as time, of there being a space X and a group G acting on it. And we want to understand the action of G on X as group cohomology. So the group G that we are curious about is the automorphisms of a fixed formal of a formal group of height H over a characteristic P field. So that is the group of interest. And the space of interest is this space, which is the spectrum associated to this power series ring. Now, if you've never seen SPUF before, it is essentially just spec, but for power series rings. Just when you take co-limits of spec, it doesn't behave well. And so we take instead this thing called SPUF, which kind of remembers the topology of this limit on rings. Okay. Cool. So
hi, excuse me.
Yeah.
SP, does that deal with symplectic?
I'm sorry, SP
form?
here?
Yeah.
So
no, it's spec, but it's a special. Sorry.
It's okay. Yeah, so SPUF is kind of like, so okay, if you were just looking at a power series ring, this can always be written as a limit of polynomial rings. And if you then apply spec to that, you would hope that you could just take a co-limit of spec and get kind of what you want to be working with. But unfortunately, spec doesn't behave well with respect to limits. And so we have to instead consider something that does behave well with respect to limits. And this is called the formal spectrum. And it's the formalness is just coming from the fact that we're taking kind of like that the limit, taking limit outside of spec doesn't commute. And this turns out to be the appropriate kind of co-limit in schemes. So
Okay.
it's not associated with the symplectic group.
Sure.
Although I do think it is a very interesting question, like what the analog of symplectic form should be in characteristic P. And I think people are thinking about that more seriously recently. But that's not what we're talking about on this talk. Maybe in another talk.
Thank you.
Okay. So let's consider how we might visualize this action. It's just me kind of sillily writing down a visualization, which is we're starting with this formal group H. This lives over spec K, where K is the coefficient ring of H. And we can then, and let's say we have some given deformation of the formal group H, G, which is this pair, G, which is living over spec R, and I, which is this guy here, which is the way that we reduce the spec K thing to a spec, the spec R thing to a spec K thing. Okay. Sorry. All right. And so this map, sorry. So how does the action, I was talking about the fact that we have an action by the automorphisms of H, which is just precomposition on I, and this is just me visualizing, okay, well, if we're in some point of this moduli space of deformations, we apply the action of the automorphism of H, we get sent to another thing in this moduli space of deformations. And this action fixes just the identity, which is the, not deforming anything at all, and it moves everything else around freely. So let's talk about this group where of automorphisms of a given formal group H. So how big is this group? What does it look like? So this is a profinite group. It's a very big. And for a fixed height in prime, it looks like the units of this division algebra, which is, we take, again, if you want to think of, if you haven't seen the Witt vectors before, you can think of Witt vectors of Fp to the H as Zp adjoin a particular root of unity. Then we adjoin this generator S, and we say that S to the H is equal to P. Again, H is this height phenomenon that I talked, this height invariant, which is coming from looking at the kernel of the multiplication by P map size at infinity, the rank at infinity. Sorry, at the identity. And we also asked that if you have a elements of this ring look like power series in S, or I guess it's a polynomial in S. And if we want to move something from the Witt ring past S, it picks up an action by Frobenius. And then we ask for the units. Okay, so this is a giant, big profinite group. So let us now ask, what do the finite subgroups look like? So the finite subgroups look like, they look very different depending on if P-1 divides the height or not. So let's look at kind of what they look like. So if it divides the height, if it does not divide the height, it's just a cyclic group, which is co-prime to P. If it does divide the height, then it is a cyclic group that there is a non-trivial P-CELO subgroup. And this is very exciting because if we take the cohomology in characteristic P, or P-adically, and we have a co-prime to P group that we're taking the cohomology of, then there will be no cohomology above H0. So if we want to understand something that has interesting topological information, the group cohomology, we probably want to look at something whose group cohomology exists above H0. And so we want to look at things that have P-CELO subgroup. Okay, so the reason that I'm mentioning that, let's examine this group and understand what this group look like is that if we want to actually write down and understand the action of the full Morava stabilizer group, which is this which is the name that topologists have for automorphisms of a formal group. This is a massive, massive thing, and it's very complicated. There are ways that we can understand the action of this rationally. So if we take the group cohomology and tensor with Q, this is in an upcoming paper. And we know that the action rationally is in fact trivial. But we don't know the action integrally at all. And trying to get a handle on it is very, very difficult. And we know that we can resolve a handle of the full group action using maximal finite subgroups. So let's first start there. And I'm now mentioning to you that the case of the heights that are of interest topologically, I'm claiming, are heights that are divisible by p-1. And we shall now look at what happens at those heights. Before I continue, does anybody have any questions? No? Yes? Maybe? Okay. All right, so time got away from me a little bit, so I'm not going to try to rush too much in the last bit and kind of take my time here. But the idea, so let's get to the next piece. Instead of trying to understand the full profinite group action on this formal scheme, we're going to try to understand the maximal p-CELO subgroups action on the formal scheme. And in fact, if we want to not just, even trying to understand this CPK action or CP alpha, as I've written here, action is extraordinarily difficult. And this is also wasn't known until my work, but understanding its normalizer is not that much harder. And the normalizer turns out to be the maximal finite subgroup. So, maybe in the interest of time, I'll focus more on just trying to understand the Z mod P to the K action. Okay, now we are brought back finally to inverse Galois theory, which at the beginning, as I mentioned, was you're given a group G, construct a field extension L over K such that the Galois group of that is the group G. So I'm now giving us a group, which is this maximal finite subgroup. And in fact, I'm just going to look at Z mod P to the K. And I'm asking, what finite field extension has this automorphism group? Or another way to rephrase this would be in terms of function fields. So if I have an extension if I have a curve C, which is a cover of P1, then the automorphisms of this cover.
Hi, sorry.
Yeah.
Oh, you're talking about the cover. Okay, that's good. Thank you. Sorry, I'm like, what kind of cover I was, anyway, sorry.
No, it's okay. I think there's probably a bit of a lag. And also I'm speaking without writing, which is dangerous, but unfortunately the case necessary because of the technological difficulties. So yeah. So if we have a cover of curves, C over P1, then the automorphism group of that cover will be the same as the Galois group of the function fields of the curves. So if we have a map between curves, then we will have a function field extension of one curve by the other, of the function field of one curve by the other curve. So for example, if we have a map of a curve C to P1, then we will have the Galois group, the automorphisms of that map of this cover will be the Galois group of the function field of the curve C over the function field of P1, which is just a one-dimensional function field. Okay. So that is to say that if you want to understand the so another way to state the inverse Galois theory problem would be, given a group G, construct a curve whose automorphism group is that group G. All right, so this is the task that I'm presenting for us. And I'm just going to tell you the answer. So, what is an algebraic curve that has automorphism group, Z mod P to the K? And there is a canonical answer to this. We're just going to talk about the Z mod P case, since I have approximately 4 minutes. The Z mod P case looks like this. It looks like y to the P minus y is equal to A. So this P minus 1 here is what's going to give us the automorphism group being not just Z mod P, but also this P minus 1 squared piece. But you can ignore this power of P minus 1 if you just want it to be a Z mod, like a curve with automorphism group Z mod P. The action by Z mod P takes y to y plus 1. You can see that this is an automorphism by thinking about the fact that we're in characteristic P. So y to the P minus y is actually y times y minus 1 times y minus 2 times dot 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 times y minus P minus 1. When you multiply all of those things together, this will be y to the P minus y. And so taking y to y plus 1 will just shift your root from y equals I to y equals I plus 1, which in characteristic P will take you back to the beginning. Okay. So we can now, which I wrote out here. We have y to the P minus y is equal to, y times y minus 1 times y minus P minus 1. And so how can we deform it? Well, we can consider the following deformations, which can be done apart from equations, but I'm just going to write out the equations here. And when we actually try to understand the automorphism group of this deformation, turns out you can reduce the information of this deformation to just the roots of P1. So what I mean by that is the deformations of this curve, the deformations of the curve y to the P minus y over FP over an Artinian local, over a complete local K algebra are actually just the deformations of this set can be reduced to just deforming P points on P1, which on P1 of R. So if you take a curve over FP and we consider its deformation over R, the information of the deformation is the same as just specifying P points on P1 over R. This is the claim I'm making to you without justification. And it turns out that let's see. It turns out that I'm just going to state this. It turns out that the deformation space of these Z mod P curves, as I mentioned, is equivalent to the deformation space of just P points on P1. And this space, which is actually a stack, as a Z mod P representation, is the reduced regular representation. It's the symmetric algebra of the reduced regular representation, which means that the group cohomology of the Z mod P action on the Lubin-Tate space, which is at height P minus 1, the E2 page of this spectral sequence related to the homotopy groups of spheres, is in fact just the action of Z mod P on the reduced regular representation of Z mod P, which allows you to completely compute the E2 page. And there is an analogous, you can analogously show this for Z mod P to the K. And the answer for Z mod P to the K for those heights is induced up from the reduced regular representation to Z mod P to the K. And using that, we can actually calculate the Tate cohomology of all of these. So we can calculate this E2 page. Okay, I think that's the end of my time.
Thank you. Does anyone have any questions?
Yeah, I do have a question. Thank you for the very nice talk. It was great, especially since we're running a learning seminar on deformation theory, so very apropos and very interesting. You had some, right, so you looked at those cyclic subgroups, but on your list there was a semi-direct product somewhere. Should I worry about that case or?
Oh, sorry. So let me scroll up to the list you're talking about. So you're talking about this semi-direct product of z mod p to the k?
Yeah, that one.
Yes. So, okay, what ends up happening is the group cohomology of z mod p to the k semi-direct, this other thing, acting on Lubin-Tate space, will always factor through the group cohomology of z mod p to the k semi-direct, the automorphisms of z mod p to the k.
Oh, right. It was that case where there's really only contribution from one of the pieces.
What do you mean? Sorry?
Well, was that the thing where you had some it's just because something was co-prime to something else, then we could use a simplification. You outlined the
Yes.
argument. Yeah, it's that case. I see. It kicks in that case. Yeah.
Yeah, essentially we were able to just like simplify down to the z mod to the automorphisms of z mod p to the k, and you can kind of pretty naturally change the curve that you consider by like changing a power that to be co-prime. Like you can change kind of the power at the bottom of what x is in this example. For like, you can just change the curve equation in a pretty natural way that doesn't affect the z mod p to the k action, to reflect kind of this other. All right, was your question how we incorporate this geometrically, or was your question how we
I was just wondering if if the semi-direct product was causing trouble.
So it ends up not causing trouble, which is awesome. The semi-direct product ends up being kind of something that's very natural to incorporate. I mean, I show you how to incorporate it in the z mod p case, but in the general z mod p to the k case, it's also not difficult to incorporate.
Okay, thank you.
It amounts to just changing the kind of z mod p to the k case by a couple powers. And the way that it's presented in when we consider kind of the representation, when we consider the stack that represents the moduli problem, the way that it kind of comes up, as I mentioned, we get, the symmetric algebra of the reduced regular representation of z mod p, and I can say what that is in more generality for z mod p to the k. But the reduced regular representation carries a natural action by the automorphisms of z mod p, and similarly for the z mod p to the k case.
Thank you.
Are there any other questions? I have a question actually.
Okay.
So I got to the point where you have the maximal p-silo subgroup acting on the formal scheme. And then what are you're trying to compute a cohomology associated to that action?
Yes. So I kind of outlined very early on that that we can one of the other things that I kind of skimmed over very early on is that if we have a moduli stack which satisfies certain properties, and we understand, like if we have a moduli stack and we understand a point on that moduli stack and the actions of automorphisms of that point on the moduli stack or on a neighborhood of that point in the moduli stack, what I didn't talk about was the sufficient conditions for this action in this moduli stack to kind of naturally project down to be the Lubin-Tate action. So the idea is, the way that this is connecting is that if you have a moduli stack that satisfies some properties, we can naturally look at the way that the group acts on the kind of universal curve over this moduli stack's neighborhood, project down to just how the group acts on the moduli stack itself, and then project down. And then what we'll end up getting is that the cohomology of the group that we started with acting on the ring that represents the moduli stack will be isomorphic to the cohomology of the group that we started with acting on the Lubin-Tate stack, the Lubin-Tate space. So the way that this connects is if we construct a moduli stack which is deformations of this curve, and you can show that the deformations of the stack, which is deformations of the curve, and the point that we choose, which is the curve itself's trivial deformation, that this moduli stack satisfies properties sufficient for this concatenation of functors to be the Lubin-Tate action, which is, so the Lubin-Tate action, the action of a group on a space, the action of a group on something is the same as specifying a map from the group to the automorphisms of that thing. And so the moduli stack that I mentioned of the deformations of curves allows us to factor this map from the group that we're curious about to the automorphisms of the Lubin-Tate space in such a way that we can understand the action and then follow it all the way through. And this gives us an isomorphism between a group cohomology we can actually compute in the group cohomology that we're interested in. Does that answer your question?
I think, let me just check. So you have the group of automorphisms of the formal group law.
Mm-hmm.
Wait a minute.
So we have the group of automorphisms of the formal group law. We take a Maxwell finite subgroup.
But that group, that's the Lubin-Tate group, and it's acting on the deformations of the formal group law. And so you want a homology of that group with values in the ring of functions on that thing that's made out of the width vectors.
Mm-hmm.
So you want to compute cohomology of that group on that moduli space.
Right.
Or with coefficients in the ring of functions on that moduli space.
That's right.
And then you use the theorem, which tells you that you can also compute that by looking at the action of a group on another space.
That's right.
Space.
Yes, and that moduli space is isomorphic. The thing that represents that moduli space is isomorphic to the Lubin-Tate space, and it's in fact an equivariant isomorphism. That's what allows this to be the same.
The deformations of that curve is the same thing as the deformations of the formal group law?
The deformations of the Jacobian of the curve are the same as the deformations of the formal group law.
I see. Oh.
So if you take so that's not quite true. So if you take the Jacobian of the curve, that's an abelian scheme. If you just have a curve, it's not an abelian scheme unless it's an elliptic curve. So we don't have a group structure. But now you can take the universal thing that has a group structure. That's the Jacobian. You can then complete that at the identity. That's going to be a formal group of some dimension. And the condition that we ask for it to be isomorphic, for its deformations to be isomorphic to Lubin-Tate space, is that when we take the Jacobian of the curve splits the completion of the Jacobian of the curve. So the formal group associated to the Jacobian of the curve, that formal group, which is of dimension, if you have a curve of genus G, the Jacobian will be dimension G. We want a one-dimensional formal group. And so the requirement that I have, which I did not talk about in this talk, is that the Jacobian of that curve's formal group splits as a representation, and the splitting has a one-dimensional component. And that one-dimensional component is universal, is the universal formal group of height H. And this is the only thing you require. And that automatically means that the moduli stack is also going to be isomorphic to the Lubin-Tate stack when you completed the identity. Sorry, that's a lot to say verbally. We can talk more about it if you want to hear more. But did you have kind of a follow-up question, or did I speak too quickly? Or
I think that answered my question.
Okay. So yeah, I mean, the thing that I kind of hid in the purpose of time is the fact that we require a very important, very strong condition for the moduli stack, for this like isomorphism to go through, for this kind of larger thing to end up being the Lubin-Tate space when we complete, and for this whole thing to be equivariant with respect to the action. Like the reason that we're able to factor it is that we require that the Jacobian, we look at this curve, which is living in, like, we look at the universal curve over this deformation space, and we ask that the Jacobian of that has this one-dimensional piece that splits off when we consider it as a representation of its own automorphism group. and that one-dimensional piece is universal. So that's what we require, but this is actually like way easier to check than you expect it to be. And that's what allows this to factor. Yep.
Oh, okay. Yeah. Cool.
May I sneak in another question?
Sure.
Do your results give us more leverage on computing the homotopy groups of the KH local sphere? Because I'm thinking of that usual homotopy fixed point spectral sequence, starting with the continuous group cohomology of the Morava stabilizer group with coefficients in the coefficient ring of the Lubin-Tate spectrum. And if I understand the big picture correctly, your work tells us more about the E2 term. Is that right?
That's
By
right.
analyzing what happens with finite subgroups, right?
That's right. So my work allows you to compute the E2 term for finite subgroups.
Ah, very nice. And does that give us some handle on that computation of the homotopy groups of the KH local sphere? Or?
So I mean, you still have to figure out differentials.
Right.
But
well,
yeah,
you're halfway there.
Yeah, but I mean, with it does allow you to compute the E2 page for heights divisible by p-1. So for example, for height 6 at the prime 3, which is 2 times 3, which is 3 times 2 minus 1, which is divisible by 2. So that case is thought to give you the answer to the remaining covariant invariant, for the 3 primary covariant invariant problem. And yeah, that's going to drop soon. We haven't really thought yet about how you would compute the differentials, but I know that Danny and Jolie are thinking about that. So it gives you the E2 page, but it doesn't give you more than that as far as I know.
Okay. Well,
yeah,
it's exciting. Thank you.
I guess the part that I find the most exciting about it is that you can reduce the essential complexity of these like really complicated higher height localizations of the sphere to something which is essentially the reduced regular representation of a cyclic group. That I find really, really lovely. Yeah. Sorry about the technological issues, everyone. I hope that me scrolling through an old slide talk wasn't too unbearable. And thanks for bearing with me.
Okay, thank you. I'll stop the recording.